Hi everyone, we're going to be going over loops again today. There's probably three, maybe a fourth video on this. Uh, and yes, I'm being a bit long-winded in some of these cases. I'll try not to slow down too much. We're going to be doing do-while loops and just reviewing loops in general a little bit more. And then next lecture series or next lecture should be for loops, and then we'll move on to other stuff. So I just like to point out neither here nor there. I was looking for a game loop or how we could actually talk about loops, how they actually appear, in the wild. And various video games actually use game loops. In fact, Pac-Man has or most video games you would ever design have an actual while loop that is intentionally an infinite loop or infinite loop. It's infinite because until you have some kind of condition which completely stops the program, it's designed to constantly loop around over and over again. While looking for that, though, I discovered this thing about Pac-Man. I do believe this is level 128, perhaps, maybe 256, one of those two. It turns out the original Pac-Man game could not be beaten fully. You could go up to the very last level, and if you beat that last level, you considered winning the game, but there was no, final you won Pac-Man. What ended up happening is you get to the next level, which gives you this garbage, this thing right here. In fact, and notice I knew that it was either level 128 or level 256. The reason is because I'm pretty positive that Pac-Man is using a byte or half a byte, depending on how you want to view it, a byte of data to record the level number. And at some point in time, when the number gets too big, it overflows and it gives you all sorts of weird random bugs in your program. So this is actually what that level looks like. And if you're trying to debug Pac-Man and you get to this level, this is what you would end up seeing because it is corrupting your data as a result of this. When you overflow, when you go the number is too big to be represented with one byte of information, the level number gets essentially corrupted and it screws up the game. You cannot beat the game at this point because there's too much junk in the way, and therefore it's the end of your Pac-Man game. It doesn't loop around like I think Donkey Kong loops around. So just in case you're wondering why we learned binary, that's yet another example where binary ends up coming up in weird, wonderful ways. Okay, so just a quick reminder, this is difficult for you guys. I fully understand that. I fully admit this, especially considering I'm having to crank out a large number of videos per class. I have 3 different classes this term. I have to design all new assignments because you can't do the same things you would do in other terms. Because there's a lot of moving pieces, there's a lot of moving parts, there's always a possibility I didn't explain something very clearly and or there is a mistake in something I have. Even if I don't make any mistakes, the rate in which we're going through material in this class, it's very easy to not understand something. And if I was doing a live class, the 4 of you that do talk that do ask questions in class, which I really appreciate always, those 4 people might actually ask, like, what does this mean, or why does this work? I can actually gauge the level of comprehension in a live class. I can't do that if I'm just making a video. I especially can't do that if I'm making a video at the end of July, early August. I can't predict the future. So I just want to look into the future and say, when you're watching this video, please, or any other previous videos, please ask questions when we do our synchronous time, because that's the only way I can make sure that everyone's on the same page, that you're not falling behind. So please check in, tell me if something's going too fast, something's going too slow, something doesn't make sense, or if you need another example. That's what the synchronous time is for. So neither here nor there, let's go back to what we were talking about. We are going to be looking at do-while loops this time, and also looking at one more revisit of normal loops today. So here's what we were looking at last time. In fact, this is a very, very crappy game, but this is actually what a video game actually does. A server will also do the same thing. They will use a while loop, an intentionally infinite while loop, just to make sure that it doesn't suddenly crash out on you, or that you don't stop playing the game because it went to 10,000 cases, right? You could play a video game for 2 days if you really, really wanted to. And so we could have it, I have a while loop. As long as I keep on clicking yes, putting in a Y, do I want to keep playing again and again, I will keep doing this while loop. If I put anything else in, like an N, I will stop. Okay. But in a video game, I actually want it to be an infinite loop until until some flag is set, until some variable like ready to quit, the ready to quit variable is set to 1, and in which case it would stop. It doesn't necessarily stop on any determined time. It's effectively infinite. It's indeterminate when this thing is going to stop on purpose. And a server is never supposed to stop. If you have a server serving up files, you're not supposed to necessarily have some condition that makes it stop. You just, turn off the computer, if you will. And so there are cases when I do want an infinite loop. So this would be one of those cases, or an example of one of those cases. Maybe I want to know how many loops I'm going to do in advance. So this is a guessing game, for example. While loops are really normally useful for when I do not know how many times I'm going to loop. So in this case, I have a guessing game. I could put some random value for a value. And all you're doing is guess my value, and then you put in a number, and if it's the number that they're looking for, you loop around. As you might imagine, this function might take a while, because it doesn't necessarily have to be 4. It could be negative 32,000 or something along those lines, right? There was no limitation on what the number was. You're just guessing a number, not even a number between 1 and 10. And you would go around and around until you guess the value. It's a pretty terrible game. It's indeterminate how long this thing will take. And for a video game, it looks like this, right? While the user has not won the game, for each loop turn, the player inputs things. So you move the mouse, you push the controller, you do something along the lines. The user does some kind of input. They might type on a keyboard. They might use the mouse. They might use their controllers. You check to see if the conditions are done to win. By the way, and the computer reacts, meaning it handles game logic, and it also renders or draws things on the screen. You can calculate whether the conditions are to win. If so, you put the win state to true, and then you loop around again, and you keep looping around until the win state is set to true, and then you'd stop. A game loop, in reality, is we have user input, so it's the control phase. We have a modeling phase, or where we change what the data looks like. We animate the flowers. We move Mario. We kill the enemy. We handle game logic. And then we have a drawing or rendering phase where we draw the scene. We draw Mario in the process of jumping. And we do this, let's say, 60 times a second. And we keep doing that loop thousands upon thousands upon thousands of times until there's some end state where you turn things off. And in a lot of video games, you don't ever turn it off. You just keep playing it until, like the old Nintendo games, you push power. It stopped when you pushed the power button again and killed the power, right? There was no stopping condition. So just in case you're wondering why while loops exist at all, if you can have infinite loops. There's a dependency thing that we also might have to worry about. So here's our condition that we need to satisfy. It's if the output value is less than the max value, what do we do? By the way, this is a modified version of the code from last time. The reason I'm wanting to modify it is because it's a bit more obvious, but I wanted to show a function being used for is even last time. Even if I had that little bug in the function, which we found, by the way, and we were able to deduce and work through how I could problem solve this. So here is me using mod and checking to see if that value, mod 2, is equal to 0. So is it an even number? If it's an even number, print out something. And I keep on going until I get to the max value. This is my condition, which will make me keep going or stop. The condition for whether I continue or not. While this is true, I keep going. If, however, I left out that C output value ++ line, what's going to happen? The C output value doesn't change ever, and I have an infinite loop. And so what we're trying to look at is there are cases sometimes when if I don't do this update, which is very common to do, I've forgotten this way more times than I care to count. If I have some counter or some value that I want to keep on increasing until it stops, if I forget to put this line in, I'm going to have a bad time. And so one of the things we could look at is we can change how our while loop looks, or we can take another approach. When we look at for loops, we're going to see this again. Just to keep it in mind, so we have cases where we don't want to know if it's going to stop or not. In cases when we have an infinite number of loops, well, that's normally when we want a while loop. But we want to make sure there's some way of making it stop if necessary. So essentially we have, if we do not change the thing that's controlling the loop, we get an infinite loop. So if we go back here, if I do not change this right here, I get an infinite loop. This is ultimately the thing that's controlling my loop. It's the one thing that changes for this expression here. And therefore, if I do not change C output value, then I will get an infinite loop. Those are those accidental infinite loops. The sit condition is never not satisfied, I guess. The condition is always satisfied, so we keep going. This is a big problem because essentially your program becomes unresponsive. Nothing else happens. You just do this tight little loop and you never actually stop. And you don't get any kind of feedback. You don't get a printf statement. You don't get anything. In fact, if you have an infinite loop and there's nothing in it, like, here, right? If my C output value was value 1, what happens? I don't print anything off. I don't print anything off. I keep on looping around with no printf statements, no feedback whatsoever of what went wrong. My program just hangs. And now it's up to me to go back and try and find some place where I have in a loop where I have an infinite loop. There's no way to know other. Like, you just have to manually look through your code and see which while loop is an infinite loop. Maybe put a breakpoint in there. Right? That's the reason why we have to worry about this sort of thing. If you want a really cool advanced idea, we're not going to be doing this in this course, but this is something that a lot of programmers think about when it comes to making their loop. It's the idea of convergence. The idea is that you are eventually converging or moving towards some stopping condition. You're moving towards that stopping condition by some set value. Not just, it can't be infinitely small value. It is like the distance from the stopping condition is one less each time. It's never equal, it's never greater than, it's always a little bit closer to the stopping condition. So if I have a countable number of loops, the thing that's counting eventually gets closer and closer to the stopping condition by like 1 each time, maybe by 2. But eventually you will stop if you do it that way. You need to be able to prove, and this is actually how you prove a loop will actually stop. You would have to be able to prove mathematically that you're converging towards some number and you will never bypass it. You will only get closer and closer. So it's called a measure function. You can do entire courses on this. I've taught entire courses on that. But again, if you want an infinite loop, great. You should be consciously choosing to do an infinite loop. When I'm making my loops, if I'm not choosing to make an infinite loop on purpose, I'm looking at my code and figuring out, am I getting closer to my stopping condition each and every time? Every time through the loop, if I'm not guaranteed to be getting a little bit closer to my stopping condition, I have a problem. So your job is to always convince yourself that this loop will eventually stop, that it is always getting a little bit closer to that stopping condition. That's what convergence is. And you can do this right now. Just look at your loops when you're writing them, and when you're just double checking your work, just think to yourself, am I getting closer to my stopping condition each and every time through the loop? Not sometimes, every single time am I getting closer to my stopping condition. You can do things a little bit better than what we had before. So here's the previous version of it with the cout++ down here. This is slightly better. What I could do, instead of having this C output value down here, I can actually put it in my while loop itself. So in order to avoid such situations of having an infinite loop, what I could do is actually put the update in my while loop itself. I wouldn't even do that myself. I would use a for loop if I ever in this situation, but just in case, if you want to see another approach, this is another approach. What this will do is it will evaluate whether C output value is less than or equal to C max value, and then afterwards it will increase C output value. That's what the plus plus here does. It does the evaluation, then it will plus plus afterwards. It does mean that it can get a little bit quirky in terms of like, oh, order of operations, but you're pretty much guaranteed that you're not going to have an infinite loop, because it's all you're not going to accidentally forget this line like you would accidentally forget the line down here. So this is where that comes in. All right. So what you really want is you want to make sure you have the condition itself is the only thing that. So let me read. Maybe there are cases when I want to do a while loop, but I want to make sure I always do a certain condition. So let me see here. The condition itself will always be will be the same only for some values. When the min value is 1, the output is the same, but when min value 2, the output is different. Okay. If I increment the C output value first, so plus plus C output value, I might miss the first condition. I will increment it. I'll do one less time through the loop. If you look at this here, whether I go plus plus C output value or C output value plus plus, it will actually change how this thing is done. If I increment C output value first, it might mean it should mean I do one less loop iteration. I'm missing the very first loop iteration. If I do C output value plus plus, I will increment C output value after I've done this check. Okay. I find it a little bit confusing myself, so I normally don't even do this right here. I will actually just use a for loop whenever I have a chance, and we'll see for loops very soon. But what you really need to do is just think through what your code is actually supposed to be doing every single step, and just walk through your code manually. Take some sample inputs, see what happens. In a case when I need to do it at least once, this is where another loop function comes in, another loop operation comes in. It's called the do while loop. It looks and acts almost exactly the same as a while loop. The only difference is I will do something and then I will check to see if I keep on looping. So instead of check to see if I loop and then do the operation, I will do the operation and then check. It is slightly different, and in fact this should be the same as it's guaranteeing me at least one time into the actual loop. So as I said, it's exactly like almost exactly like a while loop. The while loop will evaluate first and then it will check, and then it will, if it's true, then it will do what's inside the loop. The do while loop does something different. It goes into what my while loop would do, so it does at least one instance of that loop and then checks afterwards. So here's what a while loop looks like. Here's what a do while loop looks like, right? I do the body, then I check. If the while is still true, I loop around again. So if you need to do it at least once, a do while loop is what you would use it for. That's what you would use. So if I need the user's name and then you check to see if it's a valid name, the first thing you would get the user's name, check to see if it's a valid name, rather than get the user's name somewhere up here, then check if it's a valid name, and then loop around again, right? It's slightly different. So here would be a normal while loop, checking to see if the output is a valid output, or so let's see here. So if I'm going to, let's say I'm going to check, I'm going to have to do this at least once, irrespective of whatever the max value is. I want to do this is even thing one time, guaranteed. Okay. If I had that, I'd do something like this, right? I'd have an if statement doing the one-time guarantee, seeing if it's even, and then printing out if it's even, and then I'd do my while loop to change things around. But I don't want to replicate this code. This is the exact same code here. This part here is exactly the same as down here. If I want to print off the very first element no matter what, I don't want to use a while loop. I want to do something different. So this is where my do while loop comes in. It's if my print is outside of the body of the loop, like it is here, what I could do is make sure I do it at least once. And again, if I'm using a while loop, and let's say my message changes, I need to change it here, and I need to change it here. I don't want to do this. I want it in one place. The do while loop means I write my print statement in here one time, and if I need to change it, I just change it in one place. It means I will execute the body at least once. So here would be a do while loop in action. Notice I have a do, I have curly parentheses. I actually probably should put this on the line above. I like putting on the line above myself. I just didn't even notice that. I have a do, I have my curly braces, and then that while is part of that do while loop. I have a while, and this is the one time I put a semicolon after my while. It's the end of this whole expression here. This whole expression here from the do all the way down here is one thing, and so I finish it off with a semicolon. Okay, so this would be, I'm going to get the C output value. I'm going to check to see if the min is even or not, irrespective of what the maximum value is. And then I'm going to check if I stop, versus checking if I stop before I check to see if it's even. So right here is me doing my do while loop. And notice that my do finishes, well, I have my closing curly brace, and then I have my while statement afterwards. The while statement looks exactly like a normal while loop, though. The do sets up the loop, allows you to execute once. The if is tested no matter what the first time, and printf statement is done no matter what if the if statement is true. The loop would be tested on its condition using the while at the end. The while is only at the end, and I go to the beginning only if the condition is met. So it means I guarantee at least one instance. And the increment of C output value, by the way, in this case, only happens at the very, very end, not the first step. I don't increment it at the first step. I check at the very end. But we have the exact same problem with infinite loops. I can make a do while loop that is infinite. It's very easy. If I left off this plus plus here, I get an infinite do while loop. Here would be another example, right? I want to get the number. If you give me the number, this thing here, what's this going to be doing? I have a number, a floating point number called number, very original name. I have a floating point number named sum. They're both starting off at the value 0. Please enter a number, and then I'm going to get the value. I'm going to set the number value variable to whatever the user types in, and then I have some sum at the end that every single time through this loop, I'm going to make the sum equal to sum plus the number. All right. So let's say I put in, I type in the values 4.0, 5.0, 0.0. What ends up happening? I will enter a number. I will then get the value for number here, this variable number here, will get the value 4. So I hope I don't have something underneath it or something that's going to pop up. My sum value starts off at 0. It then becomes 4.0. It then becomes 4.0 plus whatever the next number I had here was, 5.0. And then afterwards, I print out the total sum for this thing, which would be the value 9. So actually, so it should be 9. It's 5 plus 4, right? So the total sum if I put in the 4 and a 5, the total sum would be 9, is what I would output. Notice one other little gotcha. I told you that these things could be gotchas. I think it's safe in this case, but I wouldn't trust it. While the number is not equal to 0. Well, it's very easy. If I put in a 0.0, is it 0.0? Things can get a little wonky when it comes to doubles and floats, and maybe it's 0.000001, not 0.0. In that case, That wouldn't be true despite the fact that you think it's 0 and I have an infinite loop, right? This is the kind of thing that you should worry about when you're using a double or a float. Worry about whether you're stopping on an actual number. This is normally kind of dangerous. I think it works in this case, but if it was like 0.1, oh, no, no, no. It's not going to work at all for you. The math is going to be slightly off, and so it's not going to be exactly 0.1. It'll be around 0.1. Okay, so I'm going to stop right now, and then we're going to pick up for loops next video. And for loops make our lives, at least I think, make our lives a whole lot easier. All right, talk to you soon.